In this next lesson on the ideal gas law, we're going to look at the relationship of all of the variables we've considered so far. So that's volume, temperature, moles, and pressure. The volume of a gas V is directly proportional to its absolute temperature T and moles N, and is inversely proportional to its pressure P. We can write that as a mathematical relationship using the Greek letter alpha, which means proportional to. So volume is proportional to temperature and moles, and is inversely proportional to pressure, or we could also say is directly proportional to the inverse of pressure, 1 over P. Now this can be made into an equation instead of using that proportion sign, and usually the ideal gas law is written as PV, pressure and volume, is equal to nRT. N is moles, T is temperature, and R is a new variable, which stands for the ideal gas law constant. So this is a number that we need in order to relate all of these numbers and units together. So R, the ideal gas law constant, has a value of 8.314 and has units of kilopascals and liters over moles Kelvin. So there's all the units that we have from our volume, temperature, moles, and pressure in our ideal gas law constant. So that gives us a way to relate all of those different units together. So the ideal gas law is just the relationship of volume, pressure, temperature, and moles of an ideal gas. And ideal is in quotations here because there really is no such thing as an ideal gas. We're going to look at that in the next lesson as well. Right now, let's just worry about calculations using that equation and R, that ideal gas law constant. So example number 1, we want to determine the pressure of 2.56 liter sample of helium gas at 734 Kelvin, and it contains 2.93 moles. So 2.56 liters, there's our volume. 734 Kelvin, that's temperature. And the 2.93 moles is N. So if we want to figure out pressure, then we want to rearrange our equation of PV equals nRT so that we are solving for P. So that means we need to divide both sides by volume. So after rearranging, our formula is going to look like P equals nRT over V. If you look back at all of the units that we have and the unit that we had for R, the ideal gas law constant, everything is in the proper units that we want them to be. So we don't have to do any conversions for this question. So it's just a matter of substituting in 2.93 moles for N. R, I said, was 8.314 kilopascals and liters over moles and kelvins, times by the temperature, 734 Kelvin. And all of that is going to be over top of volume, and that's 2.56 liters. So put all of that into your calculator. Units are going to cancel, and you'll have, in scientific notation, because we want 3 significant digits, 6.98 times 10 to the 3 kilopascals. Next example. This time we want to solve for temperature. So what temperature would be required to contain 1.52 moles of neon gas at a pressure of 150 kilopascals in a volume of 23.8 liters? Again, if we look at all of the numbers that we've been given, 1.52 moles, 150 kilopascals, and 23.8 liters, we have all of the units that we want, so we're not going to have to do any conversions. So this time, when we rearrange the ideal gas law, we want to solve for T. So if we start with PV equals nRT and isolate for T, we're going to have T is equal to pressure over and volume over top of moles and our constant. So pressure is 150 kilopascals, volume 23.8 liters, moles was 1.52, and ideal gas law constant 8.314 kilopascal liter over moles Kelvin. Again, just put that into your calculator. Make sure you put it in correctly and carefully. Divide by both that 1.52 and 8.314, and your answer should come out to 282 Kelvin. One final example, and in this one, we're going to have some conversions to do. So there's going to be multi-steps to this one. What is the mass of hydrogen gas present in a balloon that contains 2745 milliliters at 32 degrees Celsius and 780 millimeters of mercury? We're going to be solving for M. And if you think about the ideal gas law, it doesn't have an M for mass in the formula. What we could solve for is N, the number of moles, and then change that into mass. So look at what we've got. We have a volume that's in milliliters. We have a temperature that's in degrees Celsius, and we have a pressure that's in millimeters of mercury. All of those are going to need to be converted. So let's look at our volume first. We have milliliters, we need liters. I think this one we can probably do in our heads. 2.745 liters. We don't have to write that one out fully. For temperature, we need Kelvin. So 32.00 plus 273.15 is going to give us our Kelvin temperature. So that's going to be 305.15. We also need to convert that pressure so that we're in kilopascals. So 780 millimeters of mercury is going to have to be converted into kilopascals. So 101.325 kilopascals is equal to 760 millimeters of mercury. Those are the two equivalencies we want. So your pressure that you're going to need in your calculation is 103.9914, and there's a few other trailing decimals in that. Keep that in your calculator for your calculation. So back to our question. Now that we have all of our values in the correct units, we can start substituting in. We said because we need to ultimately calculate mass, first thing we're going to have to do is calculate moles. So rearranging the ideal gas law equation for moles, we would have pressure and volume on top, ideal gas law constant, and temperature on the bottom. So your pressure, we've just converted into kilopascals, so 103.9914 with all those other decimals still attached because you still have it in your calculator, times by the volume, 2.745 liters. Divide that by ideal gas law constant, 8.314 kilopascal liters over mole Kelvin, and multiply by absolute temperature, so in kelvins, so 305.15 Kelvin. Enter that in your calculator. Make sure you put things in the correct spot. Divide by both R and T, and you'll end up with 0.113 moles. And again, you've got some trailing decimals on that. Leave those in your calculator. Now we can change our moles into mass. So 0.113 moles multiplied by our ratio to change moles into grams. So we want grams on the top, moles on the bottom. And back in your question, if you look at what substance we have, it's hydrogen gas. Formula for hydrogen gas is H2. So make sure for molar mass we make it 2.02 grams for every 1 mole. Final calculation gives you 0.227 grams as your final answer.